All right, strap in, everyone, because today we are diving into a real head-scratcher in astrophysics.
Oh, yeah, it's a big one.
Yeah. Um, we got some fascinating stuff from you listeners, articles, research notes,
Mm.
all about dark energy and dark matter.
Yeah, a lot of people are interested in that.
But especially, there's this theory called quantized inertia. Ever heard of it?
Oh, yeah, quantized inertia or, QI for short.
QI, yeah.
Huh.
That's what we're going to tackle today.
It's a fascinating one.
Yeah, and I'll be honest, it's a bit mind-bending.
Oh, absolutely. It can be a little out there.
But that's why we're here, to break it down, have some fun with it.
Absolutely, make it understandable.
So first things first, the accelerating universe.
Right, that's the big mystery here.
The universe is not just expanding, it's expanding faster and faster.
Yeah, and that's really weird.
It is. And the evidence for this comes from supernovae.
Those exploding stars.
Yep, those are like cosmic mile markers,
Uh-oh.
And they're showing us that something is pushing the universe apart.
And not just pushing, like accelerating the push.
Exactly. It's like throwing a ball up, and instead of slowing down as it goes up, it speeds up, just keeps going faster.
Yeah, defies gravity as we know it.
It's bizarre. And here's the thing. Calculations show the acceleration is about 2 times 10 to the minus 10 meters per second squared.
I mean, that doesn't sound like a lot.
No, not on a human scale.
Over cosmic distances.
It adds up big time.
Yeah, and that leads to all sorts of questions.
Exactly. And you know what? This acceleration, it might be connected to some other weird stuff going on.
Oh, like what?
Stuff we see in galaxies, even our own solar system.
Okay, now you've got me intrigued.
Okay, so let's talk about galaxies.
All right, galaxies. Vast collections of stars.
Billions of stars all swirling around. But here's the thing, they're rotating too fast.
Too fast? What do you mean?
Faster than they should be, based on the amount of stuff we can see.
Oh, so like they're visible matter, the stars and gas?
Exactly. Like imagine you're on a merry-go-round, right?
Okay, I'm following.
It's spinning so fast the horses should be flying off. But they're not.
I see. Something's keeping them from flying off.
And that's the mystery with galaxies.
Yep.
Something's holding them together, providing extra gravity.
And this is where dark matter comes in, right?
Bingo. That's the leading explanation.
Yeah.
This invisible stuff that supposedly makes up most of the matter in the universe.
Makes sense in theory, but
But we've never actually seen it.
yeah, it's been decades of searching and still nothing.
It's frustrating.
Yeah.
And that's where quantized inertia, QI, comes in.
Ah, yes, the underdog theory.
The brainchild of physicist Dr. Mike McCulloch. And he says, hey, maybe we don't need dark matter after all.
Hold on, he's suggesting we throw out dark matter completely.
Well, not completely. More like maybe it's not the whole story. Maybe there's another explanation for this extra gravity in galaxies and even inertia itself.
Okay, now that's a bold claim. So how does QI work then? What's the basic idea?
Well, QI says that inertia, that resistance to change in motion that all objects have, it's not a fixed property.
Oh, so it's not like an inherent characteristic of matter.
Right. Instead, QI says inertia comes from an object's interaction with the quantum vacuum.
The quantum what now?
I know. It sounds a bit out there. It's basically this sea of fluctuating energy that exists everywhere, even in empty space.
Hold on, you're saying there's energy even in a perfect vacuum?
Yep. It's like a constantly bubbling, fizzing ocean of energy that permeates everything.
Wow, okay, I'm trying to visualize this. So everything is swimming in this invisible energy field.
Exactly. And it's this interaction with the quantum vacuum that gives objects their inertia, according to QI.
All right, I'm following so far. But how does this invisible energy actually create inertia?
Okay, so Dr. McCulloch uses this really cool analogy. Imagine a boat on water.
A boat on water, okay.
Now, imagine you create an imbalance of waves on either side of the boat. Like you dampen the waves on one side with something.
Okay, like a skirt hanging down in the water.
Exactly. Now, what happens to the boat?
Well, it'll move towards the side with fewer waves.
Right. And that's kind of how QI explains inertia. When an object accelerates, it creates a kind of imbalance in the quantum fluctuations around it.
So the object is like that boat being pushed by the imbalance in the quantum waves.
Exactly. And that pushback is what we experience as inertia.
That's a really interesting way to think about it. So we're all surfing on these quantum waves, and the faster we try to go, the more resistance we feel.
That's a great way to put it.
Okay, so that's how QI explains inertia. But how does this relate to those spinning galaxies we were talking about?
All right, to understand that, we need to bring in 2 more concepts. Horizons and Unruh radiation.
Horizon and Unruh radiation. Okay.
Now, when I say horizons, I don't mean like the horizon you see on Earth.
Right, not the edge of the ocean or something.
These are horizons in space-time,
Eh.
regions of space that are basically unreachable because of the speed of light limit.
So, like, there's a boundary, and beyond that, information can't travel fast enough to reach us.
Precisely. And it's these horizons that play a role in QI and how it might explain galaxy rotation.
Okay, I'm ready for the Unruh radiation part now. What is that exactly?
Unruh radiation is a fascinating concept, but it gets pretty complex.
Okay, give it a shot. I'm following along.
So basically it says that accelerating objects experience a sort of thermal bath of radiation.
Thermal bath, like they're heating up.
Well, it's not exactly heat in the way we usually think about it, but yeah, the faster something accelerates, the hotter this bath of radiation gets.
Okay. But I still don't see how this ties into the galaxies.
Hold on, we're getting there.
Yeah.
The key is that those horizons we talked about earlier, they affect this Unruh radiation.
They affected how?
They actually dampen it, like reducing the heat from the Unruh radiation on one side of the accelerating object.
Oh, I'm starting to see where this is going.
You getting it?
Yeah. So now we have this imbalance in radiation pushing back against the object, just like that wave dampening skirt on the boat.
Exactly. And according to QI, this imbalance contributes to the effect we experience as inertia.
So this is where the galaxies come in, right?
Yes. Think about a galaxy as a giant spinning object.
Okay, picture it spinning.
The outer edges of the galaxy, they're accelerating, right? And guess what? That acceleration creates a horizon effect.
Oh, so those outer stars are hitting those information barriers we were talking about.
Right. And that means they experience a different Unruh radiation effect compared to stars closer to the center.
So their inertia is affected differently because of these horizons.
Precisely. And that could explain why they're rotating faster than we expect. No need for dark matter.
Wow, okay. I'm starting to see how QI could be a game changer, but I have to imagine this isn't exactly a widely accepted idea, right?
You're right. It's a controversial theory, but it's definitely worth exploring further. So we're saying inertia might not be this fixed, unchangeable thing.
Yeah, QI really shakes things up.
It does. And it makes you wonder, like, what if we could actually manipulate inertia?
Ah, now you're getting to the really exciting part.
Right. I mean, if QI is right, it could totally change how we think about motion, maybe even lead to some crazy new technologies.
Oh, absolutely. The possibilities are huge.
Like imagine being able to control how easily something moves. You could make things super easy to move or practically impossible to budge.
Exactly. Think about it. You could revolutionize transportation, space travel.
Construction? I mean, are we talking like anti-gravity boots here? Flying cars?
Well, maybe not quite yet.
Yeah.
But the potential is definitely there.
It's like we could be on the cusp of some sci-fi stuff, all because of this weird quantum energy.
It's pretty mind-blowing. And, you know, QI might even explain some other mysteries out there.
Oh, yeah. Like what?
Remember those weird spacecraft anomalies?
You mean like the Pioneer anomaly? Where those spacecraft, Pioneer 10 and 11, they slowed down way more than they should have as they left the solar system.
Exactly. And there's also the flyby anomaly, where spacecraft get this unexpected speed boost when they fly by planets.
Yeah, those have been puzzling scientists for years.
But the QI actually offers a pretty good explanation for them. It fits the data really well.
So QI is solving mysteries that traditional physics can't. That's impressive. But if this theory is so great, why isn't everyone on board with it?
Well, it's a big shift, you know? A lot of scientists are hesitant to abandon the ideas they've been working with for so long.
I get it. It's like asking them to rethink their whole careers.
Right. And some people still think we can make our current models work, with a little tweaking.
So it's a battle of the theories, the old guard versus the new. How do we figure out who's right?
Oh, that's where experiments come in. Dr. McCulloch has proposed some tests that could really prove or disprove QI. If we can manipulate inertia the way he suggests, that would be pretty undeniable evidence.
So we just have to wait and see. But even if QI turns out to be wrong, it's making us think differently about the universe.
Absolutely. And that's always valuable. It pushes us forward. You know, there's one other aspect of QI I find really fascinating.
Oh, tell me.
Dr. McCulloch thinks QI can help us understand time better.
Time. Whoa, okay. How does inertia connect to time?
Well, it starts with the idea that time isn't absolute. It's relative, depends on the observer.
Right, like in Einstein's theory of relativity, gravity and motion can warp time.
Exactly. But QI suggests that the quantum vacuum might also play a role in how time flows.
So time is even more fluid than we thought.
It seems that way. And if the quantum vacuum affects inertia, like QI says, it's not a huge leap to think it might affect time too.
Okay, that's a lot to process. My brain needs a minute to catch up. So we've got QI potentially explaining galaxy rotation, spacecraft anomalies, and now even messing with time.
It's a lot, I
Yeah.
know, but that's what makes it so exciting. It shows how much we still don't know about the
It's
universe.
true. There's always more to learn. And speaking of learning, I think it's time for a little recap.
Sounds good. Let's bring everyone up to speed on what we've covered about quantized inertia so far.
Okay, so let's bring it all together. What have we learned about quantized inertia?
Well, it's this idea, right, that challenges how we think about motion and gravity. Pretty fundamental stuff.
Definitely. Saying inertia, that resistance to change in motion, it all comes from this interaction with the quantum vacuum.
Right, that sea of energy that's like everywhere, even in empty space.
Yeah, and the cool thing is, if QI is correct, it could explain a lot.
Oh, yeah, a lot of things that don't quite make sense with our current understanding.
Like those crazy spinning galaxies.
Hmm.
Maybe we don't need dark matter to explain them after all.
QI could be the answer.
And remember those spacecraft anomalies we were talking about?
The Pioneer anomaly, yeah, and the flyby anomaly, where those spacecraft acted all weird.
QI could explain those too.
It fits the data really well.
It's amazing how this one theory could, connect all these seemingly random things, right?
It's pretty elegant when you think about it. It shows you that the universe, it's all interconnected.
Totally. And you know what really gets me excited?
What's that?
The potential. If we can actually manipulate inertia, like 2I suggests,
The possibilities are endless.
endless. Imagine spacecraft that could, accelerate without needing tons of fuel.
Or buildings that are basically earthquake-proof.
Or even, new ways of traveling, new types of engines.
Yeah, completely different from anything we have today.
It's mind-blowing.
It is. But, we got to be realistic, too. QI is still a pretty new theory.
Yeah. And a lot of scientists are still skeptical.
Which is understandable. It's a big change.
Totally. But the potential payoff is so huge, I think it's worth investigating.
Absolutely. And Dr. McCulloch, he's actually proposed some experiments, tests that could actually prove or disprove QI.
So we might have some answers soon.
Fingers crossed.
This is what I love about science. It's always changing, always evolving.
Yeah, always questioning, always searching for new explanations.
It's exciting, but, I'm sure some of our listeners are out there thinking, okay, this QI stuff sounds cool, but where can I learn more about it?
Right. Well, I would say the best place to start is with Dr. McCulloch's work itself.
Yeah, he's written a lot about it. You can find his papers online on a site called Archive 2. It's like a preprint server for scientific research.
Exactly. He goes into all the details, the math and everything.
But don't worry, if the math looks scary, there are also some great videos and articles out there that explain QI in a more digestible way.
Yeah, for a more general audience.
The key is to, be curious.
Absolutely. Read about it, watch some videos, but don't just take everything at face value. Think critically about what you're learning.
Yeah, weigh the evidence. Consider different viewpoints. And don't be afraid to ask questions.
That's how science moves forward, by questioning and exploring.
And who knows, maybe one of our listeners out there will be the one to make the next big breakthrough in understanding QI.
I'd love to see that.
Me too. Well, that's all the time we have for today. Thanks for joining us on this deep dive into quantized inertia.
It's been a fascinating journey into the frontiers of physics. Keep exploring, everyone.
And keep those questions coming. Until next time.